In this lecture in Climate and Earth 401, I'm going to talk about the lapse rate. The lapse rate is the decrease of an atmospheric variable with height. Usually that variable will be temperature. Hence, unless otherwise specified as in this definition from the AMS glossary, the lapse rate is the change of temperature with height. It might also be the change of potential temperature, but some sort of temperature variable. If we look back into earlier lectures on the structure of the atmosphere, one of the things that we saw that is in the troposphere, we have this decrease of temperature with altitude. It's warmest down here at the surface, and it's coldest in the troposphere at the top of the tropopause. And in fact, it's coldest at the tropical tropopause. This cooling with height is related to dynamics. It's related to vertical mixing. And this cooling with height, this change of temperature with height, is called the lapse rate. Hence, we often are looking at this quantity here in the troposphere when we're talking about lapse rate. Of course, by the general definition, we have other lapse rates here, and it might be worth thinking about how do we explain the lapse rate in the mesosphere. We're going to use the potential temperature, and in this lecture I'm simply going to state the definition of potential temperature, which is Poisson's equation. The potential temperature is the temperature a parcel would have if you moved it adiabatically from some pressure and temperature to the surface of the Earth. That definition goes back to our consideration of the thermodynamic equation. If we move it adiabatically, then we are saying that we have no J term in that equation. So there's no radiation, there's no thermal conductivity, there is no heat coming into or going out of the system. Hence, the changes in temperature are going to be related to the equation of state and the relationship between pressure, density, and temperature. We're now going to consider the atmosphere explicitly to be dry. Hence, we will be talking about the dry adiabatic lapse rate. And the dry adiabatic lapse rate in a hydrostatic atmosphere, the potential temperature, theta, does not vary in the vertical direction. There's a lot packed into that. For hydrostatic atmosphere, so that dP dz is equal to minus rho g, and if it's dry and there's no heat coming into or out of the system, then d theta dz is equal to 0. That means that in a hydrostatic atmosphere, the temperature T must decrease with height because the density and the pressure are both decreasing with height. This is again similar to one of the homework problems that you did about what would be the temperature at the top of an atmosphere at constant density. And there are a number of ways you can play with the hydrostatic equation to try to understand how temperature, pressure, and density would vary under these idealized and thoroughly unrealistic situations. What we want to do is to derive the dry adiabatic lapse rate. Again, I want to remind you that you own the equation. And if you own the equation, you do have to treat the equation according to a set of rules, but you can manipulate it however you want to. One of the rules that you must keep in mind is the equal sign, which means that if you do something to one side of the equation, you have to do it to the other side to maintain that equality. And again, I'm going to say, think of derivations that we do as exploration. They're not prescribed. We don't have any hard and fast rule, though we do have, well more than a century of maybe best practices to get results that we know are useful. But even, with more than 100 years at this game, occasionally you can play with the equations and think about something you want to investigate and come up with a new method of analysis, a new approach. It's especially true if you bring in other fields, such as perhaps statistics. So all I'm going to do here is present a schematic. It would be extraordinarily tedious to go through this in detail. But what we're going to do is we're going to start with the equation for potential temperature, Poisson's equation, which you should see embedded here as theta equals to T, P naught over P, this exponent here of RD over Cp. We're going to take the logarithm of that potential temperature. Again, when we're taking the logarithm or doing exponentials in the vertical, what we're doing is we're really recognizing the exponential decrease of pressure with height. So we're taking advantage of that really very fundamental aspect of the atmosphere. We're now going to take the vertical derivative of this, so d by dz. We do d by dz on both sides. We're going to use the definition of the derivative of log x and the derivative of a constant and rewrite this equation in this form. We're going to multiply through by t. We're going to use the hydrostatic balance. We're going to use the equation of state. We're going to arrive down here at the bottom of this equation, which is that T over theta, d theta dz, is equal to dt dz plus g gravity over Cp, and this is a constant. So in this derivation, you see that this term goes away. You see that this term is rho RT over P. You should recognize that through the equation of state. That's going to be equal to 1. And then we get to this equation here. So the dry adiabatic lapse rate, the adiabatic change in temperature with height is equal to this, what we just derived on the previous page. We saw that for a hydrostatic atmosphere that was dry adiabatic, that d theta dz was equal to 0. Hence, dt dz is equal to minus g over Cp. And this g over Cp is called the dry adiabatic lapse rate, and that is approximately 9.8 or 10 Kelvin per kilometer. In a dry atmosphere, this profile would be very close to the dry adiabatic lapse rate. Remember, adiabatic does not mean isothermal. It means there is no external heating or cooling. If the atmosphere is in adiabatic balance, the temperature changes with height. Even in adiabatic motion, with no external sources of heating or cooling, if a parcel moves up or down, its temperature changes. It's worth thinking about that and then adding water to that parcel to think about how water might change that, and hence what we might call a wet adiabatic lapse rate. We use the definition of potential temperature here, and I just want to state that the potential temperature is, in fact, the thermodynamic energy equation under the assumption of adiabatic motion. Hence, if you go back to the thermodynamic equation, make the assumption of adiabatic motion, so we take a J out, then this is what the thermodynamic equation reduces to. Hence, if the atmosphere were stirred adiabatically, this is how the temperature would evolve, and that's how you would get to that lapse rate. In actuality, however, the observed temperature decline is not dry adiabatic, and I will leave it as a thought question of what are the physical reasons that this is not quite dry adiabatic. And with that, that is the end of the introduction to the lapse rate. This has been a Snowy Llama production.